So similar to what we've been doing, let's go ahead and look at electron affinity. We talked about atomic and ionic radii or size, and we saw how it was related to your electron configuration or your effective charge. We talked about ionization energy, saw the same thing, how we can discuss this and understand it based on electron configuration. We see the same thing here. Electron affinity, we are going to use those same concepts to be able to predict the trends. Electron affinity is defined as the energy change, delta E, that occurs when an electron is added to a gas phase atom. It's an exothermic process in most cases, not all. Sometimes it costs us energy, but most of the time the atom itself will give up energy to gain that electron. It's the opposite trend from atomic radius, and it follows the trend of ionization energy. But there are a lot of exceptions. Some electron affinities are positive and some are negative. This kind of throws students off. Basically, if the electron affinity is negative, that means the atom really, really wants an electron. It's willing to pay you for that electron. Negative, because it's from the perspective of the system being the atom. So the atom ends up giving away energy or paying an energy to take that electron. So when we say your electron affinity increases, we mean that it becomes more negative. It wants it even more. You do need to be able to write the equation. It's very similar to what you saw for ionization energy, except instead of the electron being a product, the electron is a reactant. And again, like ionization energy, everything is in your gaseous phase. So like Br gas plus an electron, giving me Br minus gas. The trend is not as clear as the other types that we've talked about, the other types of properties we talked about, because there are a lot of exceptions, but we can say the following. Groups 2 and 18, so your alkaline earth metals, and your noble gases, have positive or near positive electron affinities. Your halogens, group 17, have the most negative electron affinities. In order to determine how much something wants an electron, you're going to have to base these predictions on your electron configuration and your nuclear charge. Just because I know I forgot to write this down on the previous slide, and I apologize. So I said, F gas plus an electron, giving you F minus gas. The electron affinity, we write this as an E sub A, is equal to negative 328 kilojoules per mole. So fluorine is willing to pay 328 kilojoules for every mole of electrons it gains to form fluoride ions from a fluorine atom. So let's go ahead and work a few examples here. Which has the greater electron affinity, lithium or beryllium? Think about the electron configuration here. Lithium, 2s1. Beryllium, 2s2. What does that mean? Lithium has one spot. Beryllium, in order to gain an electron, lithium can put it, so lithium and beryllium, lithium can put an electron right here. Beryllium is going to have to put it into its empty 2p orbitals. Lithium will be greater because it's more likely to accept that electron. Beryllium has an empty 2p shell. It would really prefer to keep it that way, and it doesn't really want you messing with it. What about beryllium and boron? Beryllium, 2s2, boron, 2s2, 2p1. If I add an electron here to beryllium, again, it needs to go in those 2p orbitals that were empty, now are not. And boron, it's just going to put one more in its 2p orbitals. Boron doesn't much care per se, like it's not going to fight you for the electron, but it will be greater than that for beryllium. What about boron and carbon? Boron, 2s2, 2p1. Carbon, 2s2, 2p2. If I give boron one, it's just going to go into its p orbitals. But if I give carbon one, it's going to have a half-filled shell. Carbon is going to pay pretty sweet for that half-filled shell. Carbon's much more willing to pay for it than boron. What about carbon and nitrogen? Carbon, 2s2, 2p2. Nitrogen is 2s2, 2p3. So now, do I put one electron here, or do I put an electron here? Carbon is going to be more willing to pay. For nitrogen, it's going to destroy the half-filled shell, which has greater stability. For carbon, it's going to create a half-filled shell. Which is more advantageous. What about carbon or oxygen? This one gets a little tricky. So basically, do I add an electron here or here? In this case, oxygen actually wants that electron more. It's not filling that shell completely, but oxygen really wants electrons. It's the second most electronegative element there is. Electronegativity we're going to talk about later in the semester, but electronegativity is the likelihood of being able to pull electron density to itself from a bond that's being shared with another atom. But oxygen wants that electron more than carbon does. Even though carbon would have a half-filled shell, oxygen has almost a full-filled shell now. And lastly, oxygen or fluorine, 2s2, 2p4, or 2s2, 2p5. So do I want to put one electron here or one electron here? Fluorine's going to pay. Fluorine's going to pay more than oxygen does. Oxygen's going to pay a lot, but fluorine's going to pay just a little bit more because it's just that much closer to gaining a completely filled S shell, or 2p shell, but also an N equals 2 shell. So fluorine just needs one electron to be just like a noble gas.